Okay, cool. So welcome to this guest lecture on basics of graph theory. So I'll start with a short introduction. So I'm Harshit Motwani. I'm a postdoctoral fellow in Department of Computer Science. My background is more, I'm a mathematician, and my research area is like applications of algebraic geometry to computer science. And so today I'm going to cover like basics of graph theory that you need for your algorithm course. And I've been told that the graph algorithms are just starting or they have started already. So the goal of this lecture would essentially be to introduce you
完了，
to,
他英文说好一点了，听说。
uh, okay, do you have any questions? Okay, I guess it was just, okay. So the goal of this lecture is just to introduce you to the basic notations and notations of graph theory and to make you aware of the intuition of what graphs are, some and so like the contents that I'm covering here is like I'll cover the basic definitions, I'll give you some examples, I will give you some terminologies that are commonly used in this area, and then I'll cover some properties. I will introduce you to trees and their properties, and then I'll go to adjacency matrices, and I will end with graph isomorphism. So during the lecture, feel free interrupt me anytime you like, and you can ask your questions in the chat. And if anything is not clear, just you can ask the question, raise the hand, or just unmute yourself and ask anything. So before I start, I want to say something about graphs. So graphs are essentially like a combinatorial mathematical objects, and why they are important, I think you cannot find an area in which they are not used. So from natural sciences to formal sciences, including computer science, mathematics, and natural sciences, including chemistry, biology, physics, and in social sciences, it finds its application everywhere. Like I can challenge you to give me an area where they're not used. If you can come up with something, that would be really nice. So in my research life and in my student life, I've seen them being used for modeling lots of different things. If you're an applied person, you'll like that. If you're a theoretical person, you'll like that. If you are an engineer, you'll like that. I think there's something for everyone here. So it's really hard not to like this theory, and it's really important. It's really fun. You can play with examples, you can draw pictures, and like there are some really nice theorems, and there are some really nice algorithms here. So just enjoy this subject, and that's the aim of this lecture also, so that you start enjoying and you start developing the intuition for graphs, and then once you see graph algorithms, you will not be intimidated by what graphs are essentially. So this is what I aim for today. So okay, so now not wasting more time, I'll just introduce you to what is a graph. And oh, so before I proceed, everyone can hear me, right? Yes, this session will be recorded, and I will send you this recordings, and I will also share the lecture notes with you. And in this lecture notes, there will be in like I have given exercises in between. These exercises are not compulsory, but I will suggest you to do that. So because it develops your intuition, and you don't even need to submit these exercises. This is for you, and like basically so that you start enjoying this subject more. So what is a graph? So is everything fine before I proceed? Everyone is fine with this, right? Like just say yes in the chat so that I know that everyone is on the same page, and then I proceed. Cool, cool. Okay. Okay. So what is a graph? So intuitively, it consists of vertices and edges. And like I will give you the picture first. Okay, people are still joining in. So okay. So what do I mean by vertices and edges? So this is an example of a graph. So these are vertices and these are edges. Edges connect two vertices. This is the intuition. So like we will work with finite vertices and finite edges in this course. I will not go to infinite setting, and things are nice here. Like we'll just assume that this is finite. So you have finite set of vertices, and then you have edges that connects them. More formally, it is a collection of two sets, vertices and edges. Set of vertices is given by capital V, and set of edges is given by E. As I'm telling you that we are working with finite sets, the set of vertices has cardinality n and set of edges has cardinality m. And I will keep this notation same throughout the lecture. And this is also the standard notation used in the theory. So this is just one running example that I'll keep on using this again and again. And okay, there are some people still joining. Okay, cool. So then, as I've already mentioned that these are really useful things, just to be more explicit, some real world examples. So you can see social networks like Facebook or Twitter, like you can see so in the analysis of social network, people actually use graph to model them. So you can see nodes, people as nodes and the connections between other people as edges. That is one real world application that you see. The other one is coming from natural science, that is like molecular structure. So like generally people use this graph to like model all the molecules that we have. And so like the atoms can be replaced by the vertices and the bonds between the atoms can be replaced by the edges. And then it forms a very fundamental object in computational chemistry. And this is from where computational chemistry starts its modeling most of the times. The third one is coming from like a really real world problem is like traffic routing, like when you have traffic lights and like then how you distribute the traffic and how to manage traffic lights and like how to do GPS navigation where the places in the world can be described as vertices and the path from them can be given by edges and stuff like that. So it can be used for a lot of things. These are just three real world examples that comes to the mind, like without even thinking hard. But as I told you, it's very hard to find an area which doesn't have graphs in them. Like it's everywhere. Okay, so okay, now I'm coming from motivation to the theory. So example, so like uh, again following the same example, now I'm formally describing this set of vertices. So this is a finite graph. So like it has 6 vertices. So the vertex set is given by this 1, 2, 3, 4, 5, 6. These are the 6 vertices, and the edges are given like this. So edges are basically okay. I need to be more formal here. Edges are basically a subset of V cross V. So we only contain information. So it looks like this. This set looks like this. So 1, 2 is an edge, 2, 3 is an edge. Or and see, 1, 3 is not an edge. So you do not find 1, 3 here. Is this fine? Is this clear? Everyone is on the same page? Just say yes or no in the chat so that I know. Okay, cool. So this is an example of an undirected graph. So see, in this edge, I'm not giving any direction. So for me, in this set 1, 2, and 2, 1, are basically same. I'm not making any distinction here. I'm not saying that I'm not giving any direction that edge goes from 1 to 2 or 2 to 1. Basically, it's the same. So in this set, I'm not making any distinction, and this is called this is known as undirected graph. And these are the graphs that we will work with today most of the time. I will introduce you to directed graph in a second, but this is the first simple family of graphs that you see, and it's better to develop intuition from here. And now I will give you what directed graph is. So in directed graph, edges are directed. That means that here 1, 2 is not same as 2, 1. So there's one additional information coming here in the definition. So I'm giving you an arrow. This arrow is giving the direction. So when I store these edges, I make the distinction between this. So now this is not same as this graph. So here the edge is going from 1 to 2 and here edge is going from 2 to 1. So we care about the direction of arrows. We care about that information from where the edge is going. And this is called a directed graph. So let me know if you have any questions because I'm going to use this throughout. But if you have any questions, just feel free to interrupt right now. I don't mind. So if everyone is fine, then I'll proceed to some terminologies, like some common terminologies that people use. So even in your algorithms, you will see that someone will just use these terminologies to tell you what an edge, how vertices are connected and stuff like that. So every edge we'll assume has 2 endpoints. So an edge E has 2 endpoints U, V in E. So U belongs to V and V belongs to V. U belongs to the vertex set and V belongs to the vertex set. We say that an edge joins U and V if you have this in your edge set. Or we say these are like equivalent things. You say U and V are adjacent, or you say U is a neighbor of V, or you say E is incident on U or V, or you say V is incident on E. All of these statements mean the same thing. This means that your graph has an edge UV, E, which is UV. So these are just the different ways of saying the same thing. Just read through, just go through them once again with me, because like in some other courses or in some other places you might see this, so don't get confused. It just is telling you that in your graph you have U and V. That's it. If you're fine with it, I'll proceed. Just say yes or no. If you have any question, let me know. Just use chat. It's easier for me to know. Okay, cool. So there's a question that one is asking if UV is directed or not. So if so for the time being, I'm working with undirected graph. So it will be clear from you in the context. So like right now, I'm just working with undirected graph. But if I'm working with directed graph, I will tell you that this is a directed edge, and then UV is directed. I'm not using special symbols to tell you UV is directed or not. So in a directed graph, I will say that UV is not same as VU. Uh, but like it will be clear for you in the context. Like you have to see it from the context. Essentially, right now I'm just working with undirected graphs, and you can use the same terminology for directed things. But like I'll just make the difference that UV is not same as VU. Yeah. Okay. Cool. The second definition. We'll have lots of definitions, and then you will see some results, and then essentially you have to get accustomed to these definitions so that when you see the algorithms, you are very comfortable with those algorithms. So for a given vertex V in the graph, we define degree of V to be the number of edges incident on V, which essentially is like, remember, UV is incident on E is like you have to count. So degree V is just keeping the count, how many edges are coming out of V. And like, since this is not directed graph, I'm working with undirected graph, number of edges coming out or coming in is basically the same. So in the, remember, in the directed graph, you have degree out and degree in. So degree out is like number of edges going out, and degree in is number of edges going in. But like, I'm not going to make that distinction because most of the times I'll be working with undirected graph. When I'm working with directed graph, I'll make it clear. So degree of V is number of edges incident to V is like number of edges going through V. So for example, here, uh, degree of 1 is like how many edges are going through this, and this. So this is like 3. And degree of 5 is like what? 1, 2, and 3. There are 3 edges, 5, 6, 5, 1, and 5, 6, 5, 6, 5, 1, and 5, 4. So it's like 3. Just do it on your own, and we can actually fill this out for everyone. Degree of 2 is like 2. Now these are the 2 edges. Degree of 3 is 1. Degree of 4 is 1. Degree of 6 is 2. I hope this example is clear to everyone, right? Okay. So now we come to the first lemma. So this lemma says is like uh, if we take all the vertices and sum their degrees, that summation is equals to twice the number of edges in the graph. So I'll first explain it with an example. So again, I'll just keep the same running example. So degree of 1 is 3, degree of 2 is 2. Just do the same calculation as we have done, and then do the summation. So you just do the summation, you will see it's 12. And just see how many edges you have. 1, 2, 3, 4, 5, 6 edges. So basically it's 2 into 6. So this is in line with that. Is everyone fine with this terminology? Everyone fine with this definition? Before I give the proof, let me know if you have any doubts or questions. Cool. Okay. So how will we prove this? Anyone has any ideas? If like I can give you the proof. Maybe I've already shown you the main idea already, but like if you have any ideas, just write it on the chat, or like feel free to unmute yourself. I'm going to give you like 5-10 seconds before you can maybe like take 20 seconds, 30 seconds or okay. Yes, exactly. So you have to go with the counting argument. So basically, what we are doing. So we are taking each of the vertices and we are counting how many edges are going through it. So when we do it for one, we count these three edges. When we do it for two, we count this. So you see, you count this edge twice, and you do it for all the edges. So on the left hand side, you're counting how many edges are going through each vertex, but each edge is connected to two vertices. So you're counting each edge twice, and that is basically the argument. So we proceed by the counting argument. So degree, you're on the left hand side. Uh, we are counting number of edges through each vertex. That is essentially the definition of the degree, right? Degree of E is the number of edges coming through that vertex. And while you do that, you count each edge twice. So like this is essentially nothing but twice the number of edges, and you have the proof. Like just is this fine to everyone? Like is the main idea clear? Okay. Do you have any question or doubt that this would be a nice time to ask? Okay, I guess everyone is clear on that. So, okay, so now we'll come to another definition. So, what is a path? A path in a graph is essentially a sequence of vertices, like uh, sequence of vertices v0 to vk, such that vi minus 1 to vi is belongs to the edge. So, if we go to this example, running example, we have like 1, 2, 3 is essentially a path. So you have 1, 2 is an edge. You have 2, 3 as an edge is a path. But 1, 2, 3, 4 is not a path because 3, 4 is not an edge. Okay, is this clear? So like the path is just a collection of vertices such that all of this 1, 2, 2, 3, 3, 4, 1, 2, 2, 3 should be an edge. But here this is not a path because 3, 4 is not an edge. So, okay. So there are again some terminology. We say that there is a path from V0 to Vk if it's something like this. If we have a sequence of vertices from V0 to Vk such that we have adjacent edges, we say that length of path is defined as the number of edges on the path. So, for example, this path is length 2, length of this path, length 2, and okay, so for any path, we can also give a subpath. So suppose, so basically you just take us, okay, I need to give you an example again here. So let me just take, copy this and page. Okay, so if we have a path like, 5, 1, 5, we have a path like 4, 5, 1, 2, and 3. 5, 1, 2 is a subpath, is a path. Is a subpath. So basically, you see all these definitions. You can just have a running example in mind and just try to see all these definitions, and that's how you form the intuition in this area. We say that path from P to U. If there's a path from U to V, we say that V is reachable from U. For example, um, in this graph, I think all these vertices are reachable from all these vertices. This is like you take any two vertex and you can find a path. Like if you see 2 and 4, so I can give you a path like this. So this is 2 is reachable from 4. Similarly, 2 is reachable from 6, y and 5 and 2. So suppose if I add another vertex here, like this, suppose 7, and I don't draw any edge here. So we do not have any path connecting to 2 and 7. You do not have any path, so 2 is not reachable from 7, but like that will come later here, so I'll not think about this right now. Okay, and there's also one more definition that you should note is like a path is simple if all the vertices are distinct. So you can also have like some repetitions here in this collection of vertices, but we call a path simple if all these vertices are distinct. So for example, again, using the same running example, we have path 1, 2, 3, all these vertices are um, different, so it's simple. So now I'll give you a path like this 1, 6, 5, 1, 2. So it goes from 1, then goes to 6, and then goes to 5, and then goes again back to 1, and then goes to 2. So you see 1 is repeated here. So it's not simple. So this is an example of a path which is not simple. And the length of this path 1, 2, 3 is 2 because there are two edges. And the length of this path is like 1, 2, 3, and 4. Like there are 1, 2, 3, 4 edges here. So length of this path is 4. So let me know if you have any doubts or if anything is unclear. Um, just comment yes or no before. Just comment something on the chat so that I know everyone is on the same page or not. Do we call one a path? You can no. So like a path. Hmm. That's like a. So for a single vertex, we say that we have a path of length 0. So like we say it's a trivial path. It's like a notational convention. Like it depends on what kind of book and what kind of uh, people you are working with. So some people call it a trivial path, and some people call it a path of length 0 because there's no edge. Is that clear? You will see that like later you will see that it becomes important that we need to define that, but these are like notational issues. You can call that it's a path of length 0. We will call that it's a path of length 0. We will need that later. Any more questions? Okay, I think no. So then I'll proceed with the next definition. Okay, so now as we have defined cycle, now we'll define cycle. As we have defined path, we will now define cycle. So a cycle is nothing but a path in which the end point becomes same as the first point and all edges are distinct. So some more terminology, we say that a cycle is simple if other than the first point, all other vertices are distinct. A graph which does not contain any cycle is called acyclic. And again, just give you this, just modified this example a bit. So we have a cycle C1 here, 165. So because 1651, so this is connecting back. So like, actually I should create this 1651. So like 1 is coming back. And then, yeah. And we have a cycle C2 here. So like 1, 6, 5, 4, 3, 5, 1. So this is also a cycle. But remember, I'm again saying a cycle is simple if all the vertices are distinct. In this, other than the first one. So in this, all these 3 vertices are different. But in this, not all the these vertices are not all the vertices are distinct because you see 5 is repeated here. You're coming back to 5 again. So this is a simple cycle. This is not a simple, the pink one is not a simple cycle. Is this clear? Because we'll need this later. So if you have any doubts, just ask. Okay. Okay, now so far I've been working with undirected graphs. I've not given you the arrows in the graph, right? Now we'll switch gears. I'll give you definition for the same things for the directed graph. Like I'll give you a different definition for the directed cycles and what do you mean by directed acyclic graph. So a directed acyclic graph is a directed graph with no directed cycle. So all these things that I mentioned in the path, so you have a directed path in which the edges have arrows. So like, for example, if I have, okay, let me add a page here. Okay. Oops, sorry. Okay, just. So directed path would be something like you have given me a directed graph like this. This is 1, 2, and 3. So directed path would be again 1, 2, 3. But here, but something like 1, 3, 2 is not a path. So the only difference that is there now is now I'm giving you the arrows. So this is not a path because 1, 3 is not because 3, 2 is not an edge and 1, 3 is not an edge. So here 1, 2 is an edge and 2, 3 is an edge. But like for the undirected graph, it was fine because like 2, 3, 3, 2 was same as 2, 3. So, but is a directed path. So similarly, directed cycle would be something like if I give you a graph like this, 1, 2, and 3, 1, 2, and 3, you have a directed cycle. You have 1, 2, 3, 1. But if I think I'll give you the example later. Okay, and the same example is there. So a directed graph is a directed graph with no directed cycle is called a directed acyclic graph, and people represent that as DAC in the community in the literature. So in this example, you see there is no edge here, no directed cycle because 1, 2, 2, 3, but you don't have 3, 1 here. So it does not form a cycle. And but this contains a directed cycle 1, 2, 2, 3, and 3, 1. So you can follow the direction and come back to 1, but you cannot follow the direction and come back to 1 here. So this is not a DAG, this is a DAG. This is a DAG, this is not a DAG. Is this notation clear? Um, okay, good. Okay, so this will come up later. I will give you some exercises for directed acyclic graph later. So just let me know if you have any questions or anything. Um, but now I'm again going back to the undirected graphs. So we have already defined paths. So now we can talk about the connectivity. Connectivity is actually a topological property, but we'll not go into that too much. So for us, connectivity means connectivity in graphs. So we say two vertices are said to be connected if there's a path between them. I have already talked about reachability earlier, so it's just following the same kind of definition. So graph is said to be connected if all vertices are connected. So as two vertices are said to be connected, if you can find a path between them. And a graph is said to be connected if you can find a pair of, if for all pair of vertices in the graph, you can find some connected, you can find a path between them. Otherwise, you call it disconnected. So an example of a connected graph, or a running example is a connected graph because you take any two vertices in this graph and you can find a path. Take that as, if you don't see it right now, take that as an exercise. But any two vertices, you can find a path and you can reach from one vertex to another. So if you can reach from one vertex to another by following some edges, then it is connected. An example of disconnected graph, this is a disconnected graph. So all these vertices here are reachable from each other, and all these vertices here are reachable from each other. But there's no edge connecting here to here. There's no edge connecting from here to here. So there's no way you can follow an edge and reach to this. So this is not a connected graph because you can easily find two vertices which are not connected. That means there's no path connecting them. Like you cannot follow an edge from here to reach here. So this gives you one part of the graph which is connected, and this gives you one part of the graph which is connected. So this is an example of disconnected graph. Okay, now now we will talk about connected components. So if you have any question in connected in connectivity in connected graph, ask it right now because otherwise you'll be confused in the next section. I guess no. Okay. So what do we mean by connected component? So before I proceed, I need to tell you something about equivalence relation and something. So connectivity about among two vertices actually induces an equivalence relation among the set of vertices of a graph. And this is where your first exercise comes actually. So this equivalence relation is like this relation is like this. If A and B is said to be connected, we define this by this relation with this symbol, and we define this if A and B are connected. Now you have to prove that this is an equivalence relation. To prove that something is an equivalence relation, you need to check three things. You need to check whether reflexivity holds, that if you take any vertex, that vertex itself is connected to it or not. Symmetry holds, if A and B is connected, then is B and A connected, and then transitivity holds. If A is connected to B and B is connected to C, this implies A is connected to C. I'll give you some more hints and take this as an exercise, but I'll just give you some intuition for this. Okay. So if we have, okay, in this graph, for all vertices, so as someone asked that, is one a path? So one has a path of length 0. So like one is connected to one with a edge of length 0. That's the definition we use. So for all the vertices, one actually one is connected to one, two is connected to two, and stuff like and things like that. And now, because we are in an undirected setting, if one is connected to three, so you have a path from one to three, then this implies three is connected to one, because you just just go through that path in a reverse order. And so because you're in an undirected setting, that is given to you for free. So like if 4 is connected to 3, so just follow this path, suppose. You can follow the other path. You can just reverse this path and you can say 3 is connected to 4. And the third thing that you need to check is like if 1 is connected to, suppose, say 3, no, let's say, yeah. Suppose 1 is connected to 3 and 1 is connected to 4, then does this imply 3 is connected to 4? So what you need to do? You need to find a path from 1 to 3, and then you have a path from 1 to 4. So you basically have two paths coming out from 1. You just join these two paths and you get one path connecting 3 and 4. So this is what the intuition you will. So I have given you intuition in an example, and now the exercise is you do it for any general graph. You prove this for any general graph. So you have to like formalize these statements abstractly. You don't do it on an example. That's how you mathematically will proceed. You take any general graph and you argue like this, these three statements for any two vertices. For all the vertices, you have to check this. So is this exercise clear? Like, is this intuition clear? Just say yes or no. If you have question, just ask right now. Okay. So once you have defined, so if you check these three things, that essentially gives you an equivalence relation on the set. And once you have an equivalence relation, there's a property that comes out of that equivalence relation that it partitions the set. And okay. So for any set, if you have an equivalence, this is a set of vertices V. It partitions this in equivalence class. These are equivalence classes. So like this is like, so basically what do I mean by partitions? You take the union of, sorry, union of ui's I equals to 1 to k, and ui intersection uj is empty. Take this as also as an exercise, so that any equivalence relation actually partitions the set. So we are working with finite sets. So basically how these equivalence classes are defined. So in an equivalence class, all these, every element here is equivalent to each other. So uh, like all these elements so if A and B, if A, B belongs to ui, then A is equivalent to B and vice versa. And you do it, and basically you get this union because you're covering all the vertices. So you get this union, and then you have this intersection is an empty. This is the most abstract thing, but like you don't need to go to the full abstraction because we're working with graphs and we're working with connected things. I will just break these exercises down for you for a graph. So like this is the main abstract thing that you get for any equivalence relation on a set, that it partitions the set on equivalence classes. So I have mentioned that this is that connectivity is an equivalence relation among vertices. So it partitions vertices among equivalence classes, and these equivalence classes are nothing but connected components. So you don't have to. So I have given you this more general picture for any set for any equivalence class, but for our course we are just working with graphs. So we just need to take care of connect, because I'm saying connectivity is an equivalence relation. It partitions the vertices among equivalence classes, and these equivalence classes we are calling connected components. So for a graph like this, for example, this is a graph, and if I am giving the connectivity as an equivalence relation, then these are the connected components. So like 1, 2, 3 is a connected component, and 4, 5 is a connected component, and their union will actually give you the entire set. And this should be disjoint. So these are connected components. Please ask question, or if you let me know if you have any questions or doubt here, because I will give you 3 or 4 exercises, and you need to have you need to understand this concept clearly, because next of the rest of the lecture depends on this. Or if you don't have, okay. So what particular part can you, shall I go with everything again, or this example? Okay, so I'm saying set of vertices are actually part, like, because connectivity is an equivalence relation. So connectivity, so that will partition your set of vertices. So a set of vertices can now be written as union of connected components. So for any graph, for example, just think of this graph. All the vertices are connected, so you'll only have one connected component here. So you do not decompose it further. But in this graph is not connected. So you can write vertices as union of connected component. This is one connected component, and this is another connected component. So in this connected component, all the vertices will be connected to each other. In this connected component, all the vertices will be connected to each other. Is that clear? That's what I'm saying. So I'm giving it to you as an example, because so this is the exercise that, so I showed you how to do that on an example, but this actually is true for any general graph. So if I give you any graph, that graph can be decomposed into connected components. That's what I'm saying. And that's what I'm actually proving, or asking you to prove, that you give any finite graph, you can write that graph as union of connected components. And that is intuitively clear, because like a graph has finite vertices. Either you can reach from one vertex to another, or you cannot. So all the vertices that you can reach from one to another is in one connected component, and so on and so forth for other connected components. So you have a set of vertices. Either you can reach some vertex from each other or not. Like either you can reach one. So these are the set of vertices that you can reach each other with connected paths. These are the vertices that can reach each other using some edges. But these two vertices cannot reach each other through any path. And that's how you decompose the graph into connected components. So these are the connected components, C1 and C2. Now is that clear? Okay. So, okay, now there are like 3, 4 exercises. These are not compulsory exercises, but these are like abstract exercises that help you understand things in more general detail. So first thing is, like, I'm asking you to prove that connected components are maximal connected sets with respect to inclusion. What do I mean by that? I will explain to you with an example again. So this is a maximal set with respect to inclusion in the sense that maximal connected set with respect to an inclusion with respect to in the sense that you cannot add more vertex to it. Like any other vertex in this is not connected to it. So this is like the biggest set that you can have. So I need to explain to you with an example, I guess. Yeah. So you have like, okay, so okay. So you have this 1, 2, these are connected. 1, 2, 3 is lying inside 1, 2, and 3 with respect to inclusion. So this is connected, this is connected, this is connected, but this is the biggest connected component. Like you cannot add any more vertex to it. And this is like maximal connected component. And the other maximal connected component is 4, and this is contained in 4, 5. You cannot add more vertex because the moment you add more vertex, it will be disconnected. So this is the this is the connected set, which is maximal in the set with respect to inclusion. You cannot add any other element to it because if you add any other element, it will make it disconnected. So like this is the biggest set that you can have by adding vertices to it. So that's what I'm saying. And I'm saying that this is true in general for all the connected components. All the connected components are maximal connected sets with respect to inclusion. And the way you prove it is like this. You essentially argue that this is an equivalence relation, and you essentially uh, proceed with this, that these are unions of this and this is intersection of this. So basically you will say that, oh, in an equivalence class, I cannot add anything more to it. This is an abstract exercise. That's why I'm saying like it's an optional exercise. And all of these are abstract exercises, but like if you can handle this abstraction, you understand everything. Otherwise, you can just think of it in an example, like just try to instantiate in an example, just try to draw a graph and see what these exercises are meaning. Just try to translate these exercises to your favorite example, and that gives you more clarity. That is why I've kept these exercises here. So the other thing that I'm asking you to prove is like all the vertices in a connected component are connected. So if I give you this example, like all the vertices in a connected component are connected. 1, 2, 3, every vertex in this are connected. 4, 5, every vertex in this are connected. The third thing that I'm asking is prove that any two vertices from two distinct connected components are uh, always disconnected. So for example, any two vertex like 4 or 3 will be disconnected, 4 or 1 is disconnected, 5 or 2 is disconnected, and so on and so forth. And I was asking you to prove it for any general graph. And if a graph has only one connected component, then that is a connected graph. So our favorite example, this has only one connected component and this is a connected graph. And this you can prove it for any general graph. So these are like the 4 exercises. Just try it with some examples and try to prove it in abstraction if you can. Uh, is there any doubt with the statements of these exercises? You can ask now. And also like feel free to email me anytime while you solve these exercises if you have any doubt from this theory later. Um, is it clear? Okay, cool. Okay, so now as we have talked about connected components for a for an undirected graph, we can do the similar thing for a directed graph, but now everything will be the path will be replaced by the directed paths here. So and similarly for the connected, okay, and similar to above, we have strongly connected components. So now we have strong connectivity instead of just connectivity because we say something is strongly connected if there's a directed path in each direction between all the vertices. You will see, I'll just show you it an example. And similar to above, strongly connected is also an equivalence relation, and it also partitions the vertex set into strongly connected components. So for example, just see this graph. First see this graph and then I'll explain it again. So if you have this kind of graph, so this graph has like, so if we take A and you see these 3 shaded things, you can reach every vertex to every other vertex using a directed graph and vice versa. So you can reach A to B using this edge. You can reach B to A using this path. You can reach A to E using this, E to A using this. So that's what I'm saying. A directed graph is called strongly connected if there's a directed path in each direction between all the vertices. In an undirected graph, you don't have the distinction of the direction of the edge. But in a directed graph, we care about the direction. And I'm asking for each pair of vertices, I need paths in both the directions. And if you have that, then we say that it's strongly connected. So it's like a much stronger thing. That's why we say it's a strongly connected thing. And being strongly connected is also an equivalence relation. So if it's an equivalence relation, it also partitions your graph into strongly connected components. So for example, this graph here, you have three strongly connected components. This one, this region, this particular collection of vertices, and this particular collection of vertices. Why? Because you see, you can reach A to F, but you cannot reach from F to A, right? So that means A and F are not strongly connected. And but F and G are, because you can read F to G and G to F. And you can see similarly that this is the case for CTA and H. So this graph, this underlying graph has three strongly connected components, which would be like A, B, E, and then you have F, G, and then you have C, D, H. These are strongly connected components. Okay. Is there any question here? Is something unclear? Um, okay. Okay. So I'm giving you this as an exercise. Take this graph, check it for all the vertices, and show that these are the strongly connected components. I've already given you hints, and you need to just argue that for any two vertices you have a path in both the directions in a strongly connected component. And you see, union of this is the entire vertex set. So it's again following the theory that I mentioned, that equivalence relation partitions the vertex. So just play around with it, and like also try some different graphs that you like. So again, whenever you're doing graph theory, always have a running example at hand, because that improves your intuition. Like you understand with example much faster than understanding the abstraction. So just play with some examples and then prove the theorems, and that's how you proceed. So, okay, again, some more definitions. So subgraph. So we say subgraph is very simple, like it just is very clear from the name. So a graph G dash G prime is given by V prime and E prime is a subgraph if the word V prime is a subset of V and E prime is a subset of V. So basically it's extension of subsets. So I'm saying a graph G prime is a subgraph of G if the vertex set of G prime is a subset of vertex set of V of G, and vertex set of G prime, which is E prime, is a subset of vertex of the edge set of E. And there's another notion called induced subgraph. See, there's a difference between subgraph and induced subgraph. You should keep that in mind. So the definition of induced subgraph goes accordingly. Like we say that G prime is subgraph. So first we need that G prime is a subgraph. And second, we need that if you have any two vertex, UV in V prime, and if UV already is an edge, then UV also is an edge in your graph G prime. I'll show you with an example. So I'm saying that first of all, you need G prime to be the subgraph. And if you have two vertices inside V prime, and okay, what is that? If you have two vertices inside V prime, and if you already have an edge in the original graph, then you should have an edge in the graph E prime. Okay, so I'll explain it with an example. So suppose you have, first of all, can you hear me? There's some disturbance happening near my surroundings. So just say yes or no if you can hear me right now or not. Okay, okay, okay. So sorry for the disturbance. So we say that we have a graph, this our running graph, and we have, so this red graph, this red thing is a subgraph. So like you take 1, 2, 3. So we have vertex set 1, 2, 3. This is a subset of this, and we have edge set 2, 3, which is a subset of this. But this is not induced because you see you have 1, 2 here, but you have 1, 2 in the original graph, but not here. So that is not induced. That's what I need in induced graph. So if you have UV inside the V prime, if UV is an edge in the original graph, then you want UV to be an edge in your induced subgraph. That's the definition of induced subgraph. So this is an induced subgraph. So 1, 2, 3, but you have all the edges corresponding to them. So here you didn't have that. So this is a subgraph, but not an induced subgraph. But this is an induced subgraph. Okay, do ask any question. Let me know if you have any question here. Uh, and or if not, then just say yes so that I can proceed. Okay, cool. So always keep this distinction in mind because like sometimes like it can be confusing. So always see that when someone is talking about induced subgraph and when someone is talking about the subgraph, that is very critical for your algorithms and everything that you do later on. So now using all the things that we have defined, like cyclic, connected, and all these definitions, I define in a special class of graph called trees. This is like one of the most important class of graphs. So what are trees? So tree is basically a connected acyclic undirected graph. So we need three things. We need it to be connected, we need it to be acyclic, and we need it to be so I'm talking about undirected graphs. So we can talk about directed trees also, but like for the time being, I'm not doing that. So an undirected acyclic, oh, and also if it is not connected, then we have something called forest. So if an undirected acyclic graph is disconnected, then we call it a forest. And forest is nothing but union of trees, which is a connected component. Okay. Spend some time. We will spend some time in this definition. So I'm saying if a graph is disconnected, if a graph is disconnected, then remember, then we can have connected components of the graph. So all these connected components are basically connected and they will be acyclic, and we are working with undirected. So connected and acyclic means we are tree because they need to be acyclic because remember the definition of acyclic, all it doesn't contain a cycle. So any subgraph of it, so this is a subgraph, it should, and this is actually an induced subgraph. This also should not contain a cycle because if it did contain a cycle, then your original graph contains a cyclic, but you have assumed that original graph is acyclic. So all these connected components are also acyclic. So it's nothing but union of trees. So okay, so we have a tree and this is a forest. Uh, okay, just wait a minute. I will just ask people to not make such a noise. Just I need to pause the record. Okay. Sorry for the disturbance. Okay. Okay. So this is a tree, which is everything is connected here, but this graph is a forest because it is disconnected, but this is all the components are acyclic and the connected components are connected. So this is a forest. It's a union of trees. Is this definition clear? Or if you have any doubts, just let me know. Just say yes or no if there's an okay, cool. Hmm. Okay. So for the tree, we have like 4, 5, 6 properties that you need to keep in mind. I'll prove some of them and I'll give hints on how to prove them. And I'll leave some of them as an exercise. And then we'll have like two more important concepts that I need to introduce you, and then we can finish this lecture. So a graph, so we are assuming that this is an undirected graph. And so these 6 statements are equivalent. So I'll just go through them one by one. So we say that graph G is a tree, which is undirected. Keep in mind, tree, acyclic and connected. That is tree. So the second thing is any two vertices, if any two vertices of a graph can be are connected by a unique simple path, like if there's only a one path between them. The third thing is if G is connected, if G is a tree, if and only if G is connected, and if you remove any edge between the graph, then the resulting graph is disconnected. So if you remove any edge from the tree, it will become disconnected. And if that is true for any graph, then that graph should be acyclic and connected. The fourth thing is like if G is connected and acyclic, then the number of edges is p minus 1. And then you have this two properties. And then the last one is if G is acyclic and if any edge is added to it, then if your graph is acyclic and if you add any edge to it and the resulting graph becomes cyclic, uh, resulting graph contains a cycle, then graph G should be a tree. So before we proceed proving this equivalence, let's go with this. Let's see how this thing is. I'll just show you over this example. Okay, so what are the things? G is a tree, it's acyclic and aconnected. Okay, so the second thing, any two vertices in G are connected by unique simple paths. You see, if you take any two vertices, vertex 6 and 5, it can only be connected by a unique simple path also, like because I can go to 2, 1, 3, and then again repeat this. I'm talking about simple path here. So 6 and 5, there's only one simple path. And 2 and 3, there's only one simple path. What is the third? G is connected, but if any edge is removed, then the resulting graph is disconnected. It's okay. So just try to remove any edge from here, it becomes disconnected. And you can check it for all the edges. What is the fourth one? If G is connected, then G is connected and the number of edges. So how many vertices we have? 6. And how many edges we have? 1, 2, 3, 4, 5, which is 6 minus 1, 5. G is acyclic, yes, G is acyclic, and the number of edges we have is 5. Okay, the last one. If G is acyclic, but if any edge is added to E, then resulting graph contains a cycle. Okay, so let's say if we draw any edge between 3 and 4, suppose. So you see this this becomes a cycle. This is not acyclic anymore. So I mean, all these things we already checked on the graph. And all these statements are equivalent. So you can define a tree using any of this statement. Like and that's what we want to prove. So is this clear? If you have any question, just ask right now before I start with the proof. On okay. Cool. So to show the equivalence, how will you proceed? So to show the equivalence, we will show the following. So we show that 1 implies 2, 2 implies 3, 4, 5, and 6, and then 6 implies again back to 1. That's how we generally show the equivalence. This is the easiest way to show this kind of equivalence. Okay, so for 1 implies 2, what are the statements? So G is a tree, that is 1, and 2. Any two vertices in G are connected by a unique simple path. So we will prove this by contradiction. So this kind of proof is like prove it by contradiction. So I'll assume that 2 is not true. And what is true? Any two vertices are connected by a unique simple path. So I'll assume that there exists more than one path connecting U and V. So if you take any two, so if you have more than one path, so this is how schematically it will look. Abstractly, this is how it will be. So there is one path U and V, and there's another path P2. Then, and this is where I'm giving you exercise. So now you see we have like a kind of cycle, right? So you take P1 and you take P2. So then you can actually find a simple cycle inside P1 and P2. And like that will give you a contradiction because we are assuming that we are in a tree and we are assuming that it is acyclic. So like just fill this gap. So the main idea is this, like assume that 2 is not true, and then if it is not true, then there are like more than one path connecting U and V. If there are more than one path connecting U and V, then you have something like this. So basically P1 contains a set of vertices of G and P2 contains a set of vertices of G. So then using these two, you form a cycle. But you have started with the assumption that this is a tree, which is acyclic and connected. So it cannot have a cycle. So that's the contradiction. So that proves that that contradicts our initial assumption. So 2 is true. So given 1, that implies 2. Okay, is this clear? I'll ask it after all of these implication. So you can just ask question right now. Okay. Is it clear to everyone? Okay, cool. So the second, now we prove this 2 implies 3. So any two vertices in G are connected by a unique path, and we want to show that if G is connected, but if any edge is removed, then the resulting graph is disconnected. So how will we prove that? So, okay, just 1 minute. What do we need to show? G is connected. If any edge is removed, then the resulting graph is disconnected. If any two vertices in G are connected. Yes. So if G is connected, then we know that there's only one path from U and V. So suppose there exists an edge UV. So if there exists a set edge UV, then that is the only edge connecting U and V, right? And since graph G is connected, so there must be some vertices connecting U, and there must be some. So like if you remove this UV, there's not any other path connecting U and V, because this is the assumption of 2, that there's only one path between any two vertices. But if you have an edge, that means that is the only path that you have between them. So if you remove them, that actually gives you a disconnected component. So that completes the proof of this. It's straightforward. Like there's nothing to prove here. Actually, this one is the most easiest thing to prove. The next one is a bit we need induction for that. So I'll give you hints for that. So if G is connected, so now we have to prove 3 implies 4. So if G is connected, but if any edge is removed, then resulting graph is disconnected, right? If G, and we need to show that G is connected and E is V minus 1. So okay, so we don't need to prove G is connected because we already have that in our assumption. So now we need to show that mod V minus 1. So we prove this by induction on V. So we just say that for the induction you need two things: base case and induction hypothesis. For the base case, we are going with the induction on the cardinality of V. So we assume that our graph has only one vertex. So if your graph has only one vertex, then it has how many edges? There's no edge because it is only one vertex. And that actually gives you V minus 1. Cardinality of V minus 1. Cardinality of edges is given by cardinality of V minus 1. What is our induction hypothesis? We assume that it is true for all vertices which is less than equals to n minus 1. That we assume that mod E is actually mod V minus 1 whenever mod V is less than n minus 1. So if we remove an edge, so okay, what we need to show? Okay, we need to show that this is for all. So we need to prove the induction, right? We know that if we remove any edge, then, and what was 3? That if we remove any edge, then the resulting graph is disconnected, right? So if we remove any edge, it disconnects in two connected components, like, because that's the definition of like connected components, because like it needs to have at least more than one connected component. And since so if you remove any edge, it gives you two connected components with vertices, set of vertices v1 and v2. And we know that by induction hypothesis, and v1 is less than our starting v1 is less than n, and v2 is also less than n. So we can just use this induction hypothesis. So edges of E1 is equals to V1 minus 1, and edges of E2 is equals to V2 minus 1. But since we have only removed one edge, so the total edge of the original graph is E1 plus E2 plus the edge that we have removed. So that is the total number of edges. You just add this and you get this. So I'll just show you it in a graph. So suppose this is the edge E, this is the graph G1, which is like, and this is the graph G2. So G1 is actually V1 E1 and G2 is actually V2 E2. So how many edges you have? And this is your original graph G. This is your entire graph G. So how many edges you have in G? E1 plus E2 plus this edge that you have removed. So this is this cardinality. And from induction hypothesis, you have that, and then you get this. Is this clear? Or not, then I can just repeat this argument again. Okay. I'll just wait for 5-10 seconds so that you digest for this. Okay, cool. Cool. So now we have to prove 4 implies 5. So if G is connected and you have E equals to V minus 1, then we have to prove that this, but like this is already given to you. So we need to prove that this is acyclic. And this is where I'm giving you some exercises. So again, prove by contradiction. And this one is an exercise for you. So I'm giving you a hint here. So assume G is not acyclic. So I'm saying that if it is not acyclic, then it must contain a cycle of some length. That's the definition of acyclic. Now you have to use the fact that G is connected. And so this cycle, the vertices that come in this cycle must be connected to some other cycle, must be connected to some other vertices. As using this fact, argue that the cardinality of this is greater than n minus 1. Because we have already know that cardinality of E is equals to n minus 1. So if you can argue that, then you have achieved a contradiction, and therefore this implies that G is cyclic, a contradiction to this initial assumption. So is this hint clear? Just take this as an exercise. I want you to prove at least one thing by your own. So this is the hint. So like I have given you the main idea. You have to go at home and formalize this abstractly. And if things are not fine, then run it on some examples. And once it goes in an example, try to make it abstractly for a general graph. I'll again go through the hint. So we have to prove that G is acyclic. So I'm assuming that G is not acyclic. So if G is not acyclic, that means it contains a cycle of some length. And now G is assumed to be connected. So you have to use the fact that vertices of G must be connected, of the cycle that you have must be connected to some other vertices. And using that, count the number of edges, and that edges count will be greater than n minus 1. But that is like a contradiction because we have that E is equals to n minus 1. So we get that G is acyclic. Okay. And then what is 5? So now we have to do 5 to 6. So if G is acyclic and E is equals to V minus 1. So we have to argue that if any edge is added to E, the resulting graph becomes a cycle. Cool. Okay. So using earlier exercises, we know that G has K connected components. So if it has K connected components, so each of those connected components is a tree. So basically you'll have if you have K connected components, then it will have V minus K edges because each connected component G, all of them, so all of them are all of them are trees. And we already shown that the vertices V1 minus number of edges is vertices V1 minus 1, V2 minus 1, and so on. So you sum them and you get total number of vertices. These are the total number of vertices. But we know from our assumption in 5 that this is V minus 1. So we get that K is equals to 1. So it must have only one connected component. That means that this is connected graph. So then adding any extra edge will create a cycle because if this is connected graph, then you already have a path from every two vertices. So if you add any other edge from these two vertices, you are actually going to create a cycle, because suppose you have U and V, so you already have a path from U and V. But if you add this edge UV, this is going to create a cycle. So that proves this. So G is acyclic, but if any edge is added to it, then the resulting graph is cycle. That's what I'm proving. So I started with the assumption that, so I'm only starting with this assumption. I'm not assuming that G is connected. So with this, I'm proving that G is connected first. And if it is connected, and if it is connected, then all the vertices are connected by some path. So if you add any edge, you are actually forming a cycle. So that is 5 implies 6. Is this clear? Um, okay, like this is like a nice argument. Like this is where I'm using the uh, connected component exercises, like the connected component intuition that I've told you. Okay, now the final implication, which is like 6 implies 1. What is 6? G is acyclic, but if any edge is added to it, then the resulting graph contains a cycle. We need to prove that G is 3, but we already have acyclic, so we just need to prove that it is connected. Okay. Okay. So take any two. Okay, again the same idea will work. So we need to show that G is connected. Take any two vertices. We know that adding creates a cycle. So adding anything creates a cycle. Now, if adding anything, any edge is creating a cycle, then there must exist a path, right? This is the thing. Like if you have two vertices and you know that adding UV creates a cycle. So adding UV creates a cycle, so there must exist some path P1 connecting U and V. That actually proves that because we have not specified U and V, we're working without loss of generality with any U and V. So basically we are having path from any U and V, because that's what it is there in 6, that uh, if you add any edge, I'm not specifying which edge. So I have said that, oh, take any two vertices and add any edge UV here. I'll just need to. So if you have U and V, and I'm saying if I add this edge E, then this forms a cycle. If there is a cycle, like, so if this creates a cycle, then this cycle must contain a path from U to V. So we prove that this is connected. So this completes the proof of these 6 statements. What I want you to do after you go back from this lecture is go through each of them, try to reason it with yourself, like try take a pen and paper and try to write all these proofs on your own, and try to see if you can do it more as formally as you can. That would be a good exercise. Oh, sorry. Okay, now I not just there are like 2 remaining concepts, and then we can finish this lecture. So with a graph, and these 2 concepts will be used for your algorithms. Yeah, I will upload all the notes. I will send you the notes. So like in Canvas, everything will be there, and the recording will also be uploaded. So don't worry about that. And I will also share some references, some more references that you can read. So, so for a graph, the adjacency thing, like with a, okay, so what is a graph? You have vertices and edges. Edges contains the information which two vertices are connected. So either I give you that in a set notation, and or I can give you it in a matrix notation. You will see in your algorithm course when this notation is actually important, but for the time being, I'll just telling you this notation. This actually comes up easily when you compute the shortest paths and things like that between two graphs. So for a graph G with vertices V1 to Vn and edges E1 to EM, adjacency matrix is defined as follows. So I define a matrix and its elements of this matrix as follows. Aij is 1 if you have an edge between Vi and Vj. Otherwise, it's 0. And this is an n cross n matrix. So this is an n cross n matrix. So we have, so again, just look into this example. we have this graph. So we have like 4 vertices. So we have a 4x4 matrix. And we populate this entry by 0 and 1 whenever we have an edge. So we have an edge between 1, 2. So we say 1 here. We have an edge between 2, 3. So we say 2, 3. We put 1 here. So you say 2 and 3. A2, 3 is 1. We have an edge between 3, 2. So you put 3, comma 2. This is 1. You don't have an edge between 2 and 4. So you see you have 2 comma 4 is 0. So simply you do it for all the vertices and then you get this adjacency matrix. So that is just another way of storing the graph information. So either I give you a graph as a list of vertices and edges, or I give you an n cross n matrix. This is an adjacency matrix. Both of these things contain the same information. You will see sometimes this is better, sometimes this is better. But like there are certain operations that you can do on matrices. There are a lot of linear algebra that you can do on these matrices, and there are lots of things that can be done with these matrices. And this becomes a really good connection between matrices and graph theory. Is this notation clear? Just say yes or no so that I'll. Okay. Cool. So finally, the last example, the last concept is graph isomorphism. So an isomorphism is defined for objects, but like here, uh, we are restricting only to graphs. So we have two graphs. So it's a map between two graphs. It is first of all a bijection between the set of vertices, and it has special. First of all, it is a bijection. Oh, sorry. It is a bijection between set of vertices, and it has this property. If UV is an edge of graph G, then FU and FB is an edge of graph H. If you can find such a map between two graphs, then these graphs are said to be isomorphic, and this is the notation that we use. And yeah, we say that these graphs are isomorphic if there is an isomorphism. So if you can find a bijection between set of vertices and this extra condition, that whenever you have an edge U and V in the original graph G, you have an edge FU and FV in the original graph H. That is basically the definition of isomorphism. Example, you have two graphs here, A, B, C, D, and you have two graphs here, H, 1, 2, 3, 4. You see these two graphs looks different. But I tell you that these are isomorphism. So to show that something is an isomorphism, you need to give me a bijection between set of vertices. So you can actually obtain H by relabeling G, right? You can say A to 1 and B to 2 and so on and so forth. If you can do that relabeling and give me that relabeling, that is essentially equivalent to giving that map F. So I'm only doing the relabeling. I'm not changing the edge structure. So keep that in mind. Isomorphism is saying that you're giving a map from set of vertices to set of another vertex, which is a bijection, but you also keep in mind that you don't disturb the incidence relations between the vertices. That is important for graph isomorphism. So find the isomorphism between G and H. This is the last and very easy exercise. I have already given you a hint. You have to give me a bijection between set of vertices such that it preserves that if A and B, so suppose if you give a map between G and H, such that if A, so suppose I'm asking you to find a map F. So F of A suppose goes to 1 and F of B goes to 2 and so on and so forth. Suppose F of B goes to 2. So you need to show that if AB is an edge, then F of A, F of B should be an edge of H. So you need to find such a map. I'm already giving you hint for the first two vertex, find the other two. Basically, I'm asking you to find a relabeling such that that works. And you can try it for other graphs and so on and so forth. So this is graph isomorphism. If you have any questions, ask it here.